Yes, sir.
For the first question on homework, were we using a time? Well, what equation were we supposed to use? Because I got confused of using time independent.
Okay, so let's see, is this, homework is today 2.5?
Yes.
Okay, so the first problem,
Yes.
okay, I gotta see the equation, remind me, equation 2.32. I have it.
Yeah.
So it's
A to the A to the IKX minus the to T.
Oh, it's so fun. My friend did that one online.
Okay, so you're given this wave function. Let's see, so what was your question about it?
Well, like I just got confused in the actual working out of PFX because I remember you did something similar to that.
Okay. In this case, I'm going to factor out. Find it and let's simplify it a little bit like this. Is that okay? So far, I just factored out the time dependence.
Yes.
I haven't started lecture yet, don't worry, you're just coming in and answering questions. Now, this is a good time for you all to ask questions, by the way. And to get the probability, what do we do?
Psi star psi.
So what is psi star? It's a complex conjugate of everything. Now, A is a general complex number. You don't know anything more about it other than that it's complex. So you can't simplify that other than just to write A star. What is the complex conjugate of E to the IKX?
Negative I.
Everywhere there's an I. This out. Everywhere there's an I. It's the sign of the I. Now let's multiply these two things together. All right. These two things are going to immediately cancel, right? So the time dependence goes away in this particular case. And so now we have four terms that we have to multiply. We have two terms by two terms, we just expand it out. So there's going to be four terms. This is, so A times A star, I'm going to write like this. And this times this again gives 1. And then I get a term which is B star. This gives 1 again. Now I get the cross terms. I get AB star and 2 IKX. And then I get A star B minus IKX. But yeah.
I thought you said in the homework that omega is actually, you make all the omegas
I
negative.
did. Didn't I?
Well, if you make the omega in the book, it's omega t minus kt. So if you make omega negative, therefore you
If
back
you
up.
look right here, just look at sign of the. Oh, okay, this first term, okay, I got the k's in the wrong place. This should be minus k here. Plus k, that's what I did wrong. No, it's plus here and minus here, there we go. Okay, so it's minus here, plus here. Okay, so it's time independent. This particular superposition has no, the probability has no time dependence. And that's because the two frequencies are actually the same frequency for both modes. Did that answer your question?
Yes. Thank you.
So Ms. Pilarski happened to get trapped by me because she brought her viola in. And so I've asked her if she would please demonstrate a harmonic. So just to remind you, a harmonic, remember the string, the piano string, or viola, viola string, or any string under tension. Let's see. different equation than the Schrodinger equation. Remember the wave equation that we're looking at here, the wave equation for a string under tension. Well, I want to get, here we go. The wave equation for the string under tension, and we would have the endpoints would have to be 0. So h here is the deflection of the string. And this comes from applying Newton's second law to little bits of the string all the way along the end of the string. The curvature of the string, this piece provides a force upward or downward. Part of the string that's curved downward will be pulled down. Part of the string that's curved downward will be pulled up. And then the second derivative is the acceleration. So that's where this wave equation comes. Okay, and then we want to match this to the boundary conditions. So with the deflection, the string is clamped on each end, so the deflection has to be 0. And so I wrote down the solutions for this equation, and we found that the frequency is proportional to the wave number. And the wave number had to be such that an integer multiple of half a wavelength is equal to L. So an integer multiple of half a wavelength is equal to L. So the modes are like this. This is n equals 1, equals 2, equals 3. As in this diagram. 1, 2, 3, 4. Okay. The frequency is then proportional to n. So omega sub n, the frequency of the nth mode is n times the base frequency, omega 1, which is the lowest frequency that the string is producing. So we could excite just the lowest mode, but in musical instruments, you never really just excite just a pure mode. Get mixtures, and that's what gives the instruments their characteristic sound. So I've asked Ms. Stolarski if she could excite the viola in this mode. Actually do both. First the ground and then harmonic, so you can hear it. I haven't had this demonstration before.
So you make the.
Oh, hold on. Let's do the demonstration. Hear that? First the bass and then the harmonic. How did you excite the harmonic?
Press all the way down to press like halfway.
Halfway. You press halfway. If you're pressing at the midway point, you can't excite the bottom mode. Right? The bottom mode has its greatest deflection in the center. She's holding it so it doesn't vibrate there. Please do that again. Watch your finger. That interval is a harmonic. The frequency is exactly twice the first frequency. Thank you very much. Okay. Do you have a question about the string?
Yes, sir. And lambda over 2 equaling out. That's true because you want to make the boundary condition, right?
Yes.
Okay, that's why you make that in there.
Yeah, this can be satisfied if you have a sinusoidal wave whose half wavelengths are integer fractions of the total. Right? If you look at this is a half wavelength right here. Equals L, so that's n equals 1. Now this is a complete wavelength, so n equals 2. Now this is 3 half wavelengths, all equal to L. 1, 2, 3 half. This one's 3 halves. 3 lambda over 2 is equal to L. There are 3 half wavelengths. Here's 1 half, here's another half, making the whole wavelength, but there's another half. Okay? It's down. Okay, now when I showed this to you the other day, I didn't have prepared them. I thought, oh man, I should have done it. Let's do a superposition. I've taken the first 4 modes. Now I'll put them all in with equal weight. Somehow the bow is attacking the string to do this. I don't know how to do it in practice. But this is then how the string would start off, and now I'm going to animate. And this. I'm going to play it though. Slosh is back and forth. So the string is up and down. If you look at any one place here, let's pick the middle. Follow what the middle part of the string. It's down, it's a little bit up, oh, up, down again, almost up. It's not oscillating with one simple frequency. Any given part has a complicated up and down motion. And then all of those complicated motions are all coordinated among all the parts, but each part has a motion which is not simply sinusoidal. In fact, there are 4 frequencies that contribute to the motion of each part. Okay, now this is different than what you're going to do for the particle in the box in some very important ways. The first is we have a different wave equation, which means we'll get a different dispersion relation. The relationship between the frequency and the mode number. But also, you're going to be calculating probability. Probability is never negative. Right? So this is going to be different than the Schrodinger equation, but there's some similarities. And one of which is that there is a time dependence to the mode. And you have a superposition for the probability. There's a time dependence even if I just have one mode in the string, it goes up and down, right? It's really simple. So there's still a time dependence to that. Oh, wait. Red board. Should I pause now? I gotta wait for it to cool down. Oh, man. So this is a diagram back in chapter 1, and it's a good thing to review at this point because we're focusing on something pretty narrow here. So this diagram is similar to what we did with properties, where we categorized properties. This is a classification of substances. So it shows you how we can organize what we know of things that exist, substances that exist. So at the very beginning, of course, all of these are substances. They're all matter. They're all material. Matter means changeable. So these are all physical substances. The first division has to do whether it's massive or not. The only, well, a non-massive substance. For a while, neutrinos were thought to be massless, but now apparently not. They have mass, small mass. Not many examples in this category except for quantum. Just a massless substance between other massive bodies. So there may be other candidates for non-massive substances if possible. The other is massive substances. And in that case, we're going to be talking about quantum mechanics. So this is applying to all massive bodies. What we're doing with the Schrodinger equation apparently applies to all massive bodies. When we're talking about, there is a quantum mechanics of the plana, but there we're talking quantum field theory because we're describing quantization of the fields that exist in the plana. And quantum gravity is there with a question mark, simply because we don't know whether it's quantized or not. If it isn't quantized, it's an exception, because everything else that we know is quantized. So quantum gravity remains a mystery. There's no experimental confirmation of quantization of gravity. And the theory itself is problematic, probably because quantum mechanics has been so confused in the past. And then he's breaking down the different massive substances, their various characteristics, weak Forces, we're not going to consider here, but those are forces that take place in the nucleus, for example. If I take just a free neutron, it will decay into a proton, electron, and neutrino. That decay occurs by a weak interaction. So it's similar to, but different than electrodynamics, electromagnetism. Then some acid bodies can have charge. And also there's a strong interaction, which is what binds the nucleons together. And the parts of the proton, of course, are bound together by the strong force. Okay. And so he's going on down to talking about then living things, non-living things, elementary, non-living things, non-elementary, whether living things are sensorial or not, whether they have an intellect or not. So this is a very broad sweep here, trying to talk about things. So we're talking about things really at that highest level. There are parts or substances which are themselves up here, but then we're also talking about elementary things like an electron. Yes.
Will we, is this strong and weak thing, is that covered in this book?
No.
Okay.
No.
What would that consider, what physics area would that consider?
Particle physics.
Okay.
You would consider it in a modern physics course. Some of you will be taking a modern physics course in the next spring. Yeah, 35. You would consider that in a modern physics course. As part of now, the general subject is called the standard model, which has worked very well, but there are still challenges to the standard model. But the interrelationship between the weak, the electromagnetic, and the strong is covered in the standard model. The standard model is a highly mathematical subject, and so you can't get really very deep into it at this level. We don't do it at all in this book. Yes, sir.
That's new, right? Lowercase new? The B looking thing?
Where? Over here?
Charge.
Yeah, neutrinos.
So the B stands for neutrino?
Yeah.
Okay.
The nu stands for neutrino. Okay. Let's see. And then finally, oh, I can't read this. It says. Here are the particle in the box states. So let's review those. So I'm going to write them down again. So we have a different differential equation now for a particle in a box. We're going to consider the Schrodinger equation. And we could apply the same technique to the string that we're doing for the Schrodinger equation. We start off with the time-dependent equation. We use capital psi to deal with a wave function of both x and t, so we haven't yet separated out the time dependence. Inside of the box, there is no potential. So it looks like the Schrodinger equation for a free particle, except what? How is it not like a free particle? Yeah, the potential is infinite outside the box, which means, what does that do to the wave function?
It sets a boundary.
Yeah, exactly. So we have boundary conditions that the wave function must equal to 0. Very similar to the string. So we have this condition, and actually psi of x 0 for all x outside of the box. So we just stop writing outside of the box, right? You just, in the context of the particle in the box, remember the wave function vanishes outside of the box. Is that hard to read? Okay. So. Okay, and then we went through this. We went through this is the time. Which one is this? The time dependent, time independent. This is the time dependent Schrodinger equation, right? Because it has time dependence here. Then we are going to search for pure modes. Seek pure mode solutions. And could have done this with the string equation too. A particular form is sinusoidal in time. It has one frequency. All the parts are moving at the same time. Okay, and then the spatial part has the boundary conditions still on it. And also outside of the block. Okay, and then we saw that this was the simple harmonic oscillator. You put this in here, you have h bar omega psi is equal to minus h bar squared over 2m. Double sum of x. This is mathematically the same equation as the simple harmonic oscillator. Can you see that? The derivative now is with respect to x, not time. So you had before in the simple harmonic oscillator, x double dot is minus k over m x. So mathematically, this is the same, except x is now the independent variable, psi is the dependent. Doesn't look the same, but mathematically it is the same. So we found solutions of this form. Pi x over L, where n is 1, 2, 3. And then the frequency that goes along with that here is determined. Omega sub n is then h bar squared pi squared over 2n L squared times n squared. So omega n is n squared times the base frequency. So this, now the first harmonic, wouldn't really, the first excited mode would be 4 times the frequency. So it'd be jumping up 4 octaves, jumping up 3 octaves above the lowest mode. You read that okay?
2 ml. It's an M.
2 mass.
Thing.
This mass for the particle in the box. As far as we know, this applies to all massive particles confined by some means to a region, where L is the characteristic length of the region, M is the mass of the particle, H bar is Planck's constant. It occurs in 2 places here. Yes, sir.
And in this case just means which. Sure.
Yeah, it indexes the mode. It's called the quantum number. In the context of Schrodinger's equation, it's called the quantum number. It's a means of indexing the modes. They're sorted by the modes they occur ordered by frequency, and so we just use an index n, which again represents how many half wavelengths fit inside of the box. So it has the same relation. The multiple of lambda over 2 is equal to L, where lambda is given here. So lambda sub n is 2L over n. Like that. Okay, so you could write this in terms of the lambda. Yes, ma'am.
Okay, omega is a natural frequency.
Yes.
Correct. Is it the same thing as the energy? Because for some reason, I have the energy written down as that equation.
There's also this relationship between the frequency and the energy that did not happen in the case of the string. This is a different kind of situation here that we're dealing with. Psi is not a displacement of some kind. It was for the string. Psi is a probability amplitude. And the psi star psi is positive everywhere. Psi is not. Psi is complex. It has real and imaginary parts. And those real and imaginary parts will oscillate.
So this is just telling us what that means. Like what it just means is that it's just the probability density of that particle inside that box
In that state.
in that state. And what is
You have for a particular mode. So pick a particular value of n. Then psi star psi will be the probability for that mode.
pure mode of what?
Of the particle in a box. The electron is moving under the guiding wave, the influence of the guiding wave.
So this is the guiding waves for mode.
What's that? It's the pure mode of the system, electron, particle, and wave, guiding wave. It's the pure mode of that combined system.
Pure mode of the entirety of the system.
Yeah.
And
Remember, psi describes particle plus wave in some way, which we're not really clear on the details about how that works. But if I take psi star psi, then I get the probability of finding the particle at a given x. Got a question? Put your hand up, John.
So the energy would equal h bar pi squared over 2ml squared times n squared.
Correct.
Then it'd be h bar, not h bar squared. Because it,
Oh, excuse me. This is incorrect. There's only one h bar here.
okay.
Then the energy has to be another h bar. Thank you. And this is all in the book, right? Reviewing what's in the book, which you've read, done some homework on.
I just want to make sure I wrote it down right.
Yeah, good, right. And don't, I mean, if you're reviewing your notes, you have a question, go to the book. I make more mistakes that are in the book. The book has, for a first edition, is relatively error-free. It's really pretty good that way. So you have a question asked. Okay, so I want to show you what the superposition, so the probability, I'm going to erase this because I'm running out of board space here. Okay. So we started to look at, well, let's just go back to the pure mode. Let's look at a pure mode. Let's look at n equals 1. Probability for that state. The square of psi 1 e to the minus pi omega 1t. Square this. Time dependence drops out. Multiply e to the minus I omega t times its complex conjugate. It's 1. So going back, that's the probability for the first state. This is called the ground state, also called the 0 point state. It's the lowest possible state for an electron under the influence of the guiding wave structure. Common, pretty common. Ground state is best. Find that you can't go below the ground. It's the lowest. Okay, now we should check a few things. Let's integrate the probability. Well, the probability, remember we keep forgetting here, I don't want to keep writing it. The probability is 0 outside the box. All right, this is only inside the box. It's like the psi 0 outside. So when we form the integral, probability is 0 except when x is between 0 and L. And now we need to look up this integral. Remember I gave you the table of integrals, it's on Canvas. Handy integrals that we'll use in this chapter. The integral gives you L over 2. So it comes out to be 1, which is good. That's what we want. And that's the reason for the square root of 2 over L in the wave functions. That constant out front will guarantee that the probability is going to be 1. Total probability. All right, how about average of x? So average of x. Again, remind yourself, probability is 0 outside, so it's 2 over L times the integral of x from 0 to L of sine squared by x over L. Okay, then you look up the integral, and that result should give you L over 2, the average x. You plot this function, looks like this. So the average, not surprisingly, is symmetrical around the center. Average will come out to be there. I forgot what the interval for average of x squared, but it's this interval, 2 over L. 2 over L x squared. Sine squared pi x over L. This is a square of the sine of 2 pi x by the argument, right? So to be clear, I'll write like this. Squared. Okay, I forgot what the answer comes out to be. But it's going to be, you can form the uncertainty in x squared. And the uncertainty in x is going to be some fraction of L. That'll be inside the box. Here's the average. It's going to be somewhere around the average. It can't be farther than L over 2. Which doesn't. Okay. Then you can do the same exercise for n equals 2. Also stationary. Probability is constant. It doesn't change in time. Calculate an average, average of x squared and an uncertainty. So for n equals 2, here's the probability for 1. For n equals 2, probability dips to 0 right in the center. So the average is going to be the same again, but there is nobody at the average. So what does that mean? Go back to the ensemble. Just repeat what we've already said several times. I prepare an electron in the box in the first excited state. N equals 2 is the first excited state. First one is on the ground state. Make 1 million copies, hand it out to everybody. Okay, everybody measure your position. Everybody gets a definite answer. I combine all the measurements into a histogram and it looks like this. So that means nobody got it right in the center. But the average is L over 2. There's nobody at the average. That will often be the case. And the width, is it going to be greater than this width? The width of this probability distribution. A little bit bigger than this. It still has an upper limit. It's a little bit bigger than this one. Yes.
So they're measuring, like they have like a time interval, they
And give everybody the same time, and in this case, it doesn't matter. The time is for pure mode. It's independent of time, right?
And how do you get this particle at that stage?
Well, that's another problem. We'll get there. How do we do that? That's an interesting question. How do we do that? That's coming. Well, one way for a hydrogen atom, I mean, there's an analog for all of this in the hydrogen atom. There's a ground state, there's excited states. So one way is to shine light on it and excite the electron, and then you can pump it up into an excited state. The question is, can you get all of it in that excited state? It has to be pure. You can't have a mixture of two states. All in the excited state. But that's in principle how you could do it. For a particle in a box, not an electron in the hydrogen atom. The principle is basically the same. Okay, so far?
So it's the energy of the system in total?
Yeah.
That's,
Well, what is it? E sub n h bar squared pi squared over 2ml squared times n squared. It's n squared times the base energy. So E sub n is the energy for the electron in the box in that pure mode. And because it's a well-defined frequency, there's also a well-defined energy. But if you were measuring energies, everybody would have the same energy. We'll talk about energy measurements later. Okay, is it coming together? This is a repetition. It's good to see it again and again. I make sure it's all in your head. Okay. Now we're going to do a superposition. We're going to find out what happens now, just like the guitar string or the piano wire, or the string under tension, we're going to now have a superposition. Something is going to be a little different here. So the wave function now, this is a solution to the time-dependent Schrodinger equation. I'm going to give you a particular one. I'm going to give you a particular superposition. How do I get there? That's the problem we got to talk about. It's coming. But if I could generate the ensembles, each member of the ensemble is in this superposition. It means that the electron is moving under a strange combination of guiding wave structure. Guiding wave structure is more complex than for a pure mode. So let's put in the wave functions here. Where omega 2, remember, is 4 times omega 1. Okay, so I'm going to show this to you. What does it look like? I'm going to use my mathematic here to plot. So first I'm going to plot the wave function. Right, here's the wave function. It's complex. Here's the wave function. It's complex. It has real and imaginary parts. The real part of this is cosine. The imaginary part of this is sine. Right? This is already real here. So the imaginary parts come from the sine omega 1t and the sine omega 2t. So if t equals to 0, the imaginary part is 0. But it's not going to be 0 for very long. The real part is the cosine. Cosine here. So I'm going to animate for you what the wave function looks like. Real and imaginary parts. The blue part is real. The gold part is imaginary. Slow it down a little bit. Now, remember, you could pick any one part of this and watch it, say the real part at some location, and you'll see that there's actually 2 frequencies. It's not simple sinusoidal motion. It's a combination of frequencies. Yes?
When you're talking about the 2 different frequencies, like kind of superposition, can you think of it as like the string itself is moving at a frequency and the whole thing is moving at a frequency?
No, it doesn't work like that. Yeah, it doesn't work like that. They're actually 2 separate frequencies, and they're interfering constructively and destructively over time.
Right. And you were saying earlier kind of like about the power,
Yeah.
like involved with each of them, like what, like when we're doing like pure modes, are we kind of just ignoring like the power of the other frequencies?
Oh, yeah, that's right. When you focus on a pure mode, when you get it into a pure mode, not like this is not a pure mode. When you get it into a pure mode, then the other frequencies are gone. There's just one frequency. Yes, sir.
In like a wave like this, how is there a relation between the 2 frequencies?
Yeah, it's
I guess
just
that's
this.
okay, yeah.
Makes sense?
But that's for every like guiding wave.
No, this is only for a particle in a box. Yeah, this relationship, remember, comes from taking the Schrodinger equation, looking for a pure mode, and we find a bunch of pure modes, and we find the frequencies of those modes in order to satisfy the Schrodinger equation with the boundary condition. That comes out omega n is equal to n squared times omega 1. That's particle in a box only. So you could say that, you know, a lot of the Schrodinger equations contained in this relationship. Content of the Schrodinger equation boils down to, among other things, this frequency relation. Mathematics. Well, in physics, the pure modes have those relationships among each other. So the spectrum for a piano wire was omega 1, 2 omega 1, 3 omega 1, 4 omega 1, so forth. The spectrum for the particle in the box, also the energy spectrum. The frequency is omega 1, 4 omega 1, 9 omega 1, 16, 25, 36. Energy spectrum is, there's the ground state, and the first excited is 4 times that. Next one is 9 times that. Next one is 16 times that. It's characteristic of a particle in a box. So, beginning is the Schrodinger equation. That's where you start every problem. Write down the Schrodinger equation and figure out what are the conditions that are going to solve the Schrodinger equation. Frequently, we start with pure modes. Because if I have the pure modes, I can write down the general solution to the time-dependent problem as a superposition of pure modes. I haven't proven that to you. But knowing all the pure modes allows you to write down a general solution to the time-dependent problem. So knowing the pure modes is really, you're more than halfway there. Okay, so now let's look at the probability. Here's the probability. Take psi star psi, right? So I'm taking the real part squared plus the imaginary part squared. And now I'm going to plot that. Slow it down a little bit. Okay, so that takes, I'm going to take this, multiply it by its complex conjugate. And that's the animation of that result. So psi star, I'm going to flip the sign of I wherever it occurs. Okay, and then this is the same. This is the same. And then when I multiply it out, I get 4 terms. 2 of which will not depend on time. The other 2 will now depend on time. So you'll have the probability will have 2 terms which don't depend on time. And then you'll have 2 terms that depend on time. The result is that. Time dependence looks like that. Okay, now let's look at the, yeah, Mr. Bowen.
So on the graph where it's probability versus x.
Yeah.
So right around x is equal to 0.5. There's a point where it doesn't change its probability.
Yeah, you're right.
What is the significance of that?
Yeah, I'm not sure how significant it is, but you should be able to see it from these. The real and imaginary parts certainly don't obey that,
Right.
but it's saying that the sum of the squares is constant. Mr. Bob, I think, is noticing the probability right at a half. For this particular superposition, the probability at a half is equal to, probability density is equal to 1 or something like that. Right here. It's a coincidence, I think. I don't think there's any large physical significance to it. For another combination of pure modes, it won't be true. So it's not very general.
What is the probability function?
Well, okay, I worked that out. I worked all of this out at class on Friday.
Okay. I should
Right in
remember
the
that.
class. But you just take this, multiply it by its complex conjugate, you get 4 terms. This term multiplied by itself, time dependence goes away. And this term multiplied by itself by its complex conjugate, time dependence goes away. The cross terms give you the time dependence. Okay, how about the average of x? What is it doing? First, you should check the total probability. The integral of this thing at any time is still going to be 1, right? Because the probability is just sloshing around. So coming from, if it's moving from here, it's going over there, back and forth, right? So the total probability remains the same. The area under the curve is independent of time. 1. But how about the average? of x. Oscillating back. And then the average of x squared. So the width of this thing is changing in time. Okay, so in fact, the result looks like, here's the average of x as a function of time. So it comes back, repeats. The average of x is oscillating around a half. So it's going back and forth from the midpoint, back and to the left, to the right, to the left, to the right. And here's the width as a function of time. It's also oscillating. Okay. Right. What's the width? It's the standard deviation. This, which we get by taking the average of x minus the average of x squared and averaging that. This is sigma squared. Subscript because there's a standard deviation for anything measured. So this is the standard deviation for x. So it is a measure of the width of the distribution. Not the only measure of the width of the distribution, but it gives you an idea about how broad the distribution is in x around the average.
So it doesn't have any real just appear being a reason, right?
Sure.
This helps us
Yeah.
talk to.
Right. Okay, so why don't we just go ahead and work this out. Multiply this out. I did it Friday. Let's do it again. This is a particular superposition, two particular pure modes. Okay, I'm going to multiply. So this is 1 over root L sine pi x over L. 1 over root L sine 2 pi x over L. So multiply these two things together, get 4 terms, distribute over the multiplication over the addition. So I get 1 over L times sine squared pi x over L. Time dependence cancels when I multiply these. Right? Yes, sir. No, right? Pardon? 1 over L squared. No, 1 over L. It's 1 over root L here. You say up there? Yeah, it's 1 over root L. So they get 1 over L. And this, I'm sorry, this is not clear. I'll put the parentheses here. Here we go. It's the square of the sine. Okay, so, and then let's look at the second term multiplied by its complex conjugate. I get sine squared 2 pi x over L. So those are the first 2 terms. They have no time dependence. This one times its complex conjugate, this one times its complex conjugate. This would be the probability, well, except for a factor 2, this would be the probability if it were in the ground state by itself, no superposition. This would be the probability if it were in the first excited state, no superposition. Multiply this by 2. Okay, now I get cross terms. This term times this term. So I get 1 over L sine pi x over L sine 2 pi x over L. And I get e to the I 3 omega 1 together and substituted omega t that is omega 4 omega 1. And then let's do this way. I get exactly the same thing. Spatial part is the same. Okay, so I get 4 terms. I can combine the last 2 terms here. What is e to the I 3 omega t plus e to the minus I 3 omega 1 t? No, it's not 1. It's not multiplied, it's added. It would be 1 if you were multiplying, but those 2 terms are added.
Would it not be the hyper?
Well, not hyperbolic.
If you,
Okay, cosine. Just cosine. These are imaginary. We're adding the 2 complex, pure imaginary exponentials, trig functions. Okay, so this would be 2 cosine 3 omega 1. So the entry that comes out to be this. So when you do this at home, put your notes away. Study your notes and put them away. Do this on your own. Right? Study the notes well enough that you can do it on your own without the notes. No point in you just reproducing this, copying it down in your homework on your own. Okay, so there's the probability function, and it has a time dependence. How do we calculate the average of? First, we want to integrate this. What does this come out to be? Total probability. Come out to be 1 if everything's done correctly. If it isn't 1, something messed up somewhere. Somebody messed up someplace. How about the average of x? The interval of x, p of x. That's going to depend on time. Well, yeah, it looks like it. So there's going to be an average of x here, which is L over 2, remember? And also this was L over 2 also. This one is not going to be L over 2, it's going to be something else. But that will give you the oscillation and the average of the time. It's going to oscillate. Notice the frequency of the oscillation. Oops, excuse me. There's 3 here. That frequency is a difference of 2 frequencies. Omega 2 minus omega 1, which for this particular problem is 3 times omega 1. So in general, there will be a difference of frequencies. For a particle in a box, for this particular superposition, that difference turns out to be 3 omega 1. That's specific. But the general result holds. The superposition is not in a stationary state. What do I mean by stationary state?
changing time.
Stationary state is not changing in time. Yeah, so this is not a stationary state. Probability is not stationary. It's not unchanging in time. It is changing in time, not a stationary state. In general, pure modes superpositions, unless all of the pure modes are themselves at the same frequency, then the probability is going to be sloshing around. And the averages will all depend on time. So what does that mean? If I make my ensemble again and this excited in this superposition, hand out 1 million copies, I ask everybody take a measurement, but I got to tell you when, because if I do it at different times, I'm going to get a different answer. Probability is going to be different. Average of the x's will be different. Width will be different. It keeps coming back. It repeats. Depends on time. Question. Is that helping? You saw it once, and then you're reading it in the book, but it's going to help just to see it again. Don't be shy about asking questions. Please ask questions. But there is something I would like to point out, kind of weird. Maybe it's a COVID thing. And this is not the only class I've noticed. Sat in on some other classes. A lot of talking going on amongst people during class while the teachers talking, students are talking. I've never had that happen before. It's kind of weird, I think. My class is intense, right? There's this flood of stuff coming at you. You don't have time. The talking, you have a question, ask me, but I've noticed this in other classes too. I don't know if it's a byproduct of COVID. We're not used to being social or something. I mean, and by social, I mean, the social context here is the teacher talking. And the students can ask questions, but not at the same time the teacher's talking. You do want to watch that. I should have said something about it sooner. I'm used to being back in class in person. But I do want you to ask questions. Questions, and don't be shy about asking questions. You may think that you're the only person in the room who doesn't understand something. I guarantee you're not. And even on that very point. But also, even if the other people think they know the answer to that question, hearing me answer it will really help them too. Solidifies their own understanding. So don't be shy about asking questions. And if we're getting off track, I'll say we got to do this later. Don't worry about that. Okay. All right. No question? Okay, so we'll see you on Wednesday.